Hey everybody, Mr. Brooks here. So we're trying something a little bit different. I'm going to see by recording on my tablet, see how y'all like that. So let me know in the comments, either by email or on the web page or YouTube page. Just let me know if you prefer this versus seeing my lovely face every single time. So I might alternate in between, especially if you guys do prefer this, and then that way you've got both me teaching in front of you and then just reading and listening as well. The nice thing is this is video capture, so it will be recording my voice, and also it will be recording as I write, so everything is going to be in real time for that, well, real time with quotes in there, real time in terms of watching it and my writing. So, all right, so today we're going to cover section 4.4, which is the constant coefficient homogeneous systems. The big thing out of this is the eigenvalue problem. So in this particular section, we will develop a method to solve first order systems in the case when the matrix A sub t is a constant matrix A. So it's only going to have constant values. There's not going to be any functions of t in there. And so we will be dealing with y prime is equal to a y. Again, this is a homogeneous system, so we don't have a plus g matrix out there with that. So let's get into things. So the eigenvalue problem. In the previous chapters, so chapters 2 and 3, and actually chapter 1 as well, we have found solutions of linear homogeneous scalar equations. So those guys are not with systems. This is the single equation that we dealt with constant coefficients by looking for solutions of the form y of t is equal to e to the lambda t. All right. And there was a couple of things that we got from that. That was the characteristic equation that came in, and we solved for those, and then found out that that was actually what generates our solutions and eventually gives us the general solution to the homogeneous scalar equations. So that's the approach that we're going to take with these guys. Except we've got to change it up just slightly. So we will look for solutions of the form y of t is equal to e to the lambda t and then x. Okay, so we're like, great, another variable. Well, that variable we've talked about before. This is represented of, well, x is an n by 1 constant vector. And lambda is some constant value. Okay, and here I am going to go ahead and emphasize that we are going to possibly be dealing with, and will be dealing with, complex values when those pop up. So here, to ensure that y of t is non-zero, so a non-zero solution, I can write that bigger, I just realized that. We require that x be a non-zero vector. Okay, so that means, so let's look at the algebra through this. Okay, so we have, let's do this in a different color. Y prime is equal to a y. So on the left-hand side, so let's focus just on the left-hand side, we would have y prime. We would replace that with e lambda t x, and we'd take the derivative of it. Well, this is equal to e to the lambda t, the derivative of it, times x. And the reason I'm able to do that, think about what x is. X is a non-zero vector, so it's in its constant values that are coming. So think of it as a constant multiple. So we're able to pull that outside of the derivative and then take the derivative of the inside function. All right. Well, when I take the derivative of e to the lambda t with respect to t, I get lambda e to the lambda t x. And another way I could write that is e to the lambda t lambda x for that part. And now on the right-hand side, I'll do in black. Okay, we have ay, which is equal to a times our solution that we're trying to get out of this is e lambda t x, which we can move around because a is a constant function, and here we're going to interchange the a and the e to the lambda t. So e to the lambda t ax, and I'm able to move this around because a is a constant function or a constant matrix. E to the lambda t is some function that's multiplying the matrix, so I can move that to the left-hand side. So that's where the movement's coming in. And so when we combine these together, all right, so the combination, if we look at the whole thing, y prime is equal to a y, which this becomes on the left-hand side, we just stated, is e to the lambda t lambda x, which is equal to e to the lambda t ax. And since e to the lambda t is never equal to 0, we get left with the following equation, that ax is equal to, and I did move those around, lambda x, where x is a non-zero vector. So this is the eigenvalue problem. So notice now why we used lambda all the way back in chapter 2, because this was leading into what eigenvalues are, because eigenvalues or eigenvectors or eigenvalues are represented by lambda. So this is the eigenvalue problem. So these two are true if a is equal to lambda in this case. So here, lambda is the eigenvalue, and x is the eigenvector. Okay, so now we have those definitions. All right, so each eigenvector and that's x, is associated with an eigenvalue, lambda, constitutes an eigenpair. So when we talk about an eigenpair, they are of the form, and it looks like a coordinate pair, but it's lambda x. And for every eigenpair, of matrix A, the associated vector function y sub t is equal to e to the lambda t x is a solution to our system of homogeneous equations. All right. So one important note here is that eigenvectors are not, I'm going to emphasize that, unique. Okay. So what that means is if we have lambda x is an eigenpair, for A, then so is lambda ax, where A is some non-zero constant. This stems from theorem 4.2, which is the superposition principle. So this is saying, okay, if we multiply by some constant value, it's still going to be a solution. So that means that the eigenvectors don't necessarily have to be unique, which also helps us out because we can go for a very simple vector if we're looking for one, or some constant multiple of it as well. Okay, and those would be valid solutions. All right, so enough talking about it, so let's actually practice this. So consider the system below. We have y, so 1 prime is equal to y1 plus 2y2, and y2 prime is equal to 2y prime, or sorry, 2y sub 1 plus y2. All right, I want to show that x1 is equal to 1, negative 1, and x2 is equal to 1, 1 are eigenvectors of A, and then I want to find the appropriate lambda 1 and lambda 2. The next thing I want to do is once we find out what lambda 1 are, the two eigenvalues are, I want to find out what the two solutions, y1 and y2, are of our homogeneous system. And then the next thing is well, can I determine if this forms a fundamental set of solutions? So the very first thing that we need to do when we're solving this is we need to do a rewrite. All right, before we do that, make sure to pause the video. Again, I'm going to try to do that every single time that we come to one of these. Work on this on your own. This one might take some time, so try it out on your own, and then restart the video. Well, not restart, but press play again once you have a solution. All right. So first of all, the best thing that we need to do is get this into our format of y is equal to a, or y prime is equal to a y. Okay. So rewrite the form of y prime is equal to a y, where a is equal to, all right, look at your coefficients out in front of y1 and y2. So we have 1, 2, and then 2, 1. And then y sub t, this one's very straightforward, is just the vector y1, y2. All right, so part A. We want to use the fact that ax is equal to lambda x. All right, so we're going to do this step by step. So ax1 is equal to 1, 2, 2, 1 times what x1 was, 1, negative 1. All right. When we multiply this, we're going to do row times column. So 1 times 1 is 1, plus 2 times negative 1. And then row times column for the next element of this. So 2 plus 1 times negative 1. All right. Simplifying that, we get negative 1 and 1. Okay. We want to show that this is lambda x. So what did we multiply x by in order to get negative 1, 1 from 1, negative 1? Well, if I factor out a negative 1, so I'm factoring out a constant, I'm left with positive 1, negative 1. So this is equal to negative 1, x1. So thus, lambda 1 is equal to negative 1. And so we have the eigenpair is negative 1, x1. All right. Now we're going to do the exact same thing with x2. All right. So 1, 2, 2, 1. We're going to multiply that by 1, 1. Okay. So when we do that, I get 1 times 1, 2 times 1, and add those together, I get 3. 2 times 1 plus 1 times 1, so I get 3 again. And so if I factor out a 3, I'm left with 1 over 1, or 1, 1 as my vector. So that becomes 3x2. Therefore, or thus, lambda 2 is equal to 3. And so our eigenpair is 3x2. All right, so we just shown that these are our eigenvectors and that our eigenvalues are -1 and 3. So part B. All right, I want to show or determine that what y1 and y2 are. So I want to use the fact that we are looking for solutions of the form e to the lambda t x for any eigenpair, lambda x. All right. So for our first one, we have -1 x1. So y1 of t is equal to e to the negative t times 1 negative 1. So y1 is equal to the vector function e to the negative t, negative e to the negative t. And now for the next pair, lambda 2, x2. This is equal to 3 x2. So y2 is equal to e to the 3t times 1, 1. So y2 is equal to the vector function e to the 3t, e to the 3t. All right, and that's all we have to do. So that's what y1 and y2 are. So that part B is really straightforward. All right, part C. We stated that we need to determine if this forms a fundamental set. All right, so going back to our previous section, we're going to use the fact that psi is equal to y1, y2 forms a fundamental set if and only if the determinant of psi, let me write that a little bit better, is non-zero. All right. So psi in our case, make that a little bit big, is equal to y1, y2, or the matrix e to the negative t, e to the 3t, negative e to the negative t, e to the 3t. All right, and now we're going to find the determinant of psi. Well, we're going to multiply the diagonals and then subtract, so we're going to get e to the 2t minus negative, so plus e to the 2t, which is equal to 2e to the 2t, which is not equal to 0 for all t. All right, therefore, we can go one step further. So now that we found out this forms a fundamental set, we can say the general solution is y of t is equal to c1 times y1, which is e to the negative t, negative e to the negative t, plus c2 times e to the 3t, e to the 3t, which if we wrote this in matrix form, we get e to the negative t, e to the 3t as our first row. Our second row is negative e to the negative t, e to the 3t, times the vector c1, c2. And that's all you have to do for this problem. So So that's it for that part. Now we're going to go into our next bit. So how do we find these eigenpairs? So if I give you the vectors, that's great. However, that's not going to teach you much about where these come from. So what we're going to do is we're going to figure out how we can actually come up with our eigenvalues and our eigenvectors. All right. So we are going to start off small. We're going to deal with the 2 by 2, and then I'll show you a 3 by 3. Before we get there, we need to go over the basics of what we're looking for. All right. So the eigenvalue problem, which we've just stated before, where it's ax is equal to lambda x, consists of finding lambda and x such that ax is equal to lambda x can be rewritten as ax minus lambda x, which is equal to 0. If I factor out the x, all right, this is where it gets kind of interesting. So when I factor that out, if I'm subtracting this from a, I'm actually going to subtract it by using I here. And we're going to talk about what I is here in just a second. So since A is a matrix, I need to subtract the value lambda. Well, that's lambda times the identity matrix, which is an n by n matrix. All right. Here, we also stated that in order to find non-zero solutions, we stated that x cannot equal 0. All right. And again, here I is equal to 1, 0, 0, so forth up to 0. And this goes all the way down, 0 and down. And then it's a diagonal of 1s and everything else are 0s. So that's what the identity matrix is. Okay. So from linear algebra, and those that have it, this is okay. This is hopefully a refresher. And if you have not had linear algebra, then there's not much that you need on this part. But the biggest thing is to pay attention to what we're going to be looking for. From linear algebra, we can say that a minus lambda I x is not equal to 0 has a non-zero, so again, non-zero is important here, a non-zero solution of x if and only if the determinant of a minus lambda I is, and this is different, 0. Okay? So what this means is if we were to write this, all right, so this is different. So when we're finding out a fundamental set, we need to take the determinant and set it equal to, and we want it to be non-zero. However, if we're finding non-zero solutions of a minus lambda I, we want the determinant to be 0 of this particular matrix. Okay, this is the only one that's going to require that it be 0. Everything else is non-zero. So make sure that you note that. All right. Thus, what we want is the determinant of the matrix A11 minus lambda, A12, and let me start this back over again. So the determinant of A minus lambda I. So if I subtracted these, remember A is these constant values. So A11 minus lambda, A12, A13, and so forth up to A sub 1n. And then we have A21. Our next value would be A22 minus lambda, A23, A2 sub n. All right. So we're going to get a diagonal of subtracting lambda from your A11, A22, A33, so forth, And then everywhere else is just the normal A1n, AN2, all the way up to ANN minus lambda. We want this to equal 0. Okay. Again, it can look complicated at the beginning. Just know that this is just a general representation, and when we get into the specifics, it's very straightforward when we get there. Okay, so don't freak out about it. It's just just representing for any n by n matrix. This is what its setup looks like. All right. So by evaluating this determinant, and so I have cofactor expansion. What that means is find the determinant how we've been finding it. So, if we have a 3 by 3, then we have the minors. So we'd have A11 times its minor determinant minus A12 times its minor plus A13 times its minor. So that's what that means, and we'll see that again. So that's what the cofactor expansion is, which leads us into finding actually a polynomial equation of the form P lambda, and I'm going to write this over here. So P lambda is equal to 0, okay? Where P lambda, so I did not leave a lot of room in that type, is a polynomial of degree n of the variable lambda, which means P lambda is simply a characteristic polynomial. And P lambda equals 0 is our characteristic equation. So notice that this is almost a mirror image of what we would be dealing with a scalar homogeneous equation with constant coefficients. All right, so the eigenvalues of A are just simply the roots of this characteristic equation. All right, so that leads us into our next example. So again, pause the video, take a second, work this one out, stretch your legs, whatever it happens to be, and then let's get into this one. This one is going to take up some room. So notice I have left a lot of space in for this, and that's just because I want to make sure that we thoroughly cover this. So part A, find the eigenpairs of A is equal to 4, -2, 1, 1. Okay, very straightforward 2 by 2 matrix. Okay, and then the next part is do these solutions of y prime is equal to ay form a fundamental set. So what do we have to do for that? Well, we have to look at the Wronskian. So there's some nice things that we can get from this, and we're going to talk about that. All right. So for part A, I want to use the fact that a minus lambda I x is equal to 0, and the determinant of a minus lambda I equals p lambda. And we want this to equal 0. Okay, so this is how we're going to develop our characteristic equation. So it's a little bit more in depth than what we would normally deal with when we're dealing with a scalar, but since this is a system, it should be a little bit more intricate for it. So that's where these are going to come from. All right, so a minus lambda I. Again, all we're doing is subtracting from the diagonal. So 4 minus lambda, -2, 1, and then 1 minus lambda. Okay, so this is very easy. So again, your diagonal is the only thing that's going to be changing off of A for that part. All right, so now let's look at the determinant of A minus lambda I. All right, so when we do that, we're going to multiply by the diagonal. So we're going to get 4 minus lambda, 1 minus lambda, minus 1 times -2. Well, when we multiply this out, we are going to get 4 times 1, which is 4, minus 4 lambda, minus 1 lambda. We can just write that as lambda. And then plus lambda squared plus 2. So this becomes lambda squared minus 5 lambda plus 6. And we want this to equal 0. Okay, so let's look at our factors. Factors of positive 6 when added together give me negative 5. Well, if it's positive here and negative in the middle, that means both factors are negative. So we get lambda minus 3, lambda minus 2 is equal to 0. So lambda is either equal to 3, so I'm going to say lambda 1 is equal to 3, and lambda 2 is equal to 2. All right, so we have found our eigenvalues. Now we need to find our respective eigenvectors. Okay, so to find the respective eigenvectors, we need to solve the homogeneous system for each eigenvalue. So I'm going to write that in there, so don't worry, I'm not going to just say that. To find the respective eigenvectors. So if it's been a while, that's great. If you've not seen this before, then we're going to do this by a step-by-step process, so you don't have to worry about that. This should be a good reminder or a good lesson on how to find these guys. Now, we're dealing with a 2x2 is a lot easier than a 3x3, but there are some times when you're looking at a 2x2 solving for an eigenvector that you actually get lost in some of the calculations or how they come up with values. So a 3x3 is actually a better example when showing how to find the eigenvectors. But I'm going to try my best to describe what we're doing. All right, so what we're going to do is we're going to be plugging back in lambda 1 and lambda 2 separately into our particular equation. All right, so let's deal with lambda 1 is equal to 3. So that means, let's do this in a different color, a minus 3 lambda, or sorry, 3I, which is equal to, again, 4 minus 3, negative 2, 1, and 1 minus 3. So that means our matrix that we're going to look at now is just 1, negative 2, 1, negative 2. All right, next step. We then plug it into our problem, a minus 3I times some vector. This is the vector we're looking for, so I'm going to say x1 is equal to 0. That's what we want. So we get 1, negative 2, 1, negative 2, x1, x2 is equal to 0. All right, so if we were to solve this, so if I multiply this out, 1, negative 2, that gives me x1 minus 2x2 is equal to 0, and we have 2 copies of that. So if I were to solve this, so x1 is equal to 2x2. So that means for any choice of x2, we can find an appropriate value for x1. Okay? And vice versa, actually. If we plugged in some value for x1, we could find out an x2. The reason I say x2 was the first thing I started off with is because notice I plug in any value and then it will generate what x1 is supposed to be without having to do any division or anything like that. So that's all that I'm stating there. So for any x2, we can find the appropriate value of x1. So a non-trivial solution, so non-trivial means it's not 0. That's all we're saying. So a trivial solution here would be the vector 0, 0. So a non-trivial solution or a non-zero solution is Now this is the hard part. X1 is talking about the vector, the eigenvector for this. And I'm trying to put a script to these guys as best as possible, and I'm trying to stay block letters as much as possible when talking about the eigenvectors. If I plug in 1 for x2, that means x1 has to be equal to 2. So we let here x2 equal 1, which implies x1 is equal to 2. So that's where that's coming from. All right, now we need to do that with lambda 2 is equal to 2. Again, we want a minus 2i x2 is equal to 0. So when I plug in 2 into our equation, I'm going to get 4 minus 2, which is 2. And then 1 minus 2 is negative 1. And here I have x1, x2 is equal to the 0 vector here. All right. So when I solve this, I either get 2x1 minus 2x2 is equal to 0, or x1 minus x2 is equal to 0. So notice that those are just a constant multiple of each other, or scalar multiple. So in this situation, this implies x1 is equal to x2. So I can choose any value for x1 and I get x2 automatically. So again, a non-trivial, again, a non-zero solution is x2 is equal to, and we'll stay small, 1, 1. And again, that's coming from x1 is equal to x2. All right, so that's where those guys are coming from. Thus, our eigenpairs are lambda 1 is equal to 3, x1 is equal to 2, 1, and lambda 2 is equal to 2, x2 is equal to 1, 1. All right, so let's find out part B is do the solutions of y prime is equal to a y form a fundamental set. So for part B, again, we're going to use, or solutions are of the form y of t is equal to e to the lambda t x. All right. So y1 of t is equal to e to the 3t times its eigenvector, which is 2, 1. So therefore, y1 is equal to the vector function 2e to the 3t e to the 3t. And y2 of t is equal to e to the 2t times the eigenvector of 1, 1, giving us the vector function e to the 2t e to the 2t. All right, the next step here is, does this form a fundamental set? So that means we need the Wronskian of psi to be not equal to 0. All right, so therefore, the determinant of y1, y2, which is equal to 2e to the 3t, e to the 3t, e to the 2t, e to the 2t. This is equal to cross multiplication, so we get 2e to the 5t minus e to the 5t, which is equal to e to the 5t. And this is not equal to 0, for all t. Therefore, or thus, the set y1, y2 forms a fundamental set. On the interval from negative infinity to infinity. And that's all we have to do for that. All right. So let's go with a 3 by 3 because there's a little bit more calculations that we do and something else that's really nice that pops up with these. Now remember Abel's theorem back in section or chapter 3 where it said that if you solve, saying that on a particular interval, that for all values of, or for any value of t, that the determinant is not equal to 0 is the same thing for some value of t on the interval. So we're going to use that idea also in this next problem where if we're dealing with a particular interval, I can choose some value of t, evaluate our psi fundamental matrix, if it is a fundamental matrix, and then evaluate that determinant so we don't have to deal with functions, we can just deal with constant values. Okay, and I'll explain more as we go through that one. All right. So, same situation. So find the eigenpairs for the following matrix. A is equal to 1, negative 7, 3, negative 1, negative 1, 1, 4, negative 4, 0. All right, and now, like before, we're going to do the same exact approach, do the solutions, form a fundamental set. All right, so here, part A, again, use the idea to find our eigenvalues is the determinant of this matrix A minus lambda I. So for us, the determinant of A minus lambda I is equal to 1 minus lambda, negative 7, 3, negative 1, negative 1 minus lambda, 1, 4, negative 4, and then negative lambda. Again, you only subtract on the diagonal. All right, this is the fun part, is we have to come up with doing with our determinant of a 3 by 3. So this is the nice thing about using it on my tablet. I can highlight or circle when we're talking about the minors, and I'm going to color code them. So we're going to deal with the minor of this guy. So I'm going to have 1 minus lambda times its minor. Okay, so that's going to be negative 1 minus lambda times negative lambda minus negative 4, so plus 4. All right. And then in blue, we are going to subtract negative 7 times its minor, so negative 1 times negative lambda. So that's just going to give us lambda. And actually, let's go ahead and write those values out so you can see where they're coming from. Again, negative 1, negative lambda, minus 1 times 4. And then in black is our 3. So plus 3 times its minor, negative 1 times negative 4, minus 4 times negative 1 minus lambda. All right, so that's exactly where all these are coming from. So I'm going to write the rest of this out in red. So we're going to get 1 minus lambda times lambda squared plus lambda plus 4 plus 7 times lambda minus 4 plus 3 times 4 lambda plus 8. All right, we're going to multiply through. We're going to get negative lambda cubed minus lambda squared plus lambda squared minus 4 lambda plus lambda plus 4 plus 7 lambda minus 28 plus 12 lambda plus 24. All right, canceling out and combining like terms, so these guys are going to cancel each other out. These lambdas are going to add together to give us negative 3 lambda. So we're going to get negative lambda cubed minus 3 lambda plus 4 out of that group. All right, plus 19 lambda minus 4. So the 4's are going to cancel each other out, and then so we're left with negative lambda cubed plus 16 lambda, and we want this to equal to 0. So I'm going to factor out a negative lambda, leaving me with lambda squared minus 16 is equal to 0. So therefore, I'm going to get lambda times lambda minus 4, lambda plus 4. So thus the eigenvalues are lambda 1 is equal to 0, lambda 2 is equal to 4, and lambda 3 is equal to negative 4. So now we need to find the eigenvectors. All right. So for lambda 1 is equal to 0. So we're going to look back in again to a minus 0I. X is equal to 0, so x1. So we're going to get 1 minus 7, 3, negative 1, 1, sorry, negative 1, 0, 4, negative 4, 0. Multiply it by x1, x2, x3, which is equal to the 0 vector here. All right. So the nice thing about this is you can do row reduction on this immediately without any consequence, because you do have the 0 vector here on the right hand side. To appropriately set this up, technically you would write it as an augmented matrix. So doing a couple things here, I'm going to do row 2 plus row 1, and then row 3 minus 4 row 1. So then that way I can get zeros out in my first column. So again, didn't do anything to my top row. My second row, I'm just adding, so I'm going to get 0, negative 8, 3, 0. And then subtracting 4, we're going to get 0, positive 24, because and then negative 12 here, 0. All right. So now we can reduce these two down. At least let's reduce row 3 down as well. Actually, if we look at it real quick, row 3 plus 3 row 2, look what happens. We get 1, negative 7, 3, 0. So we didn't do anything to the first row or the second row. But notice that it's a constant multiple. All right, and we get 0, 0, 0, 0, which for us, that actually gets to tell us a couple of things. And we'll talk about that here in just a second. All right, we'll reduce down row 2 by negative 1/8 row 2. That'll help us out in some of our calculation here. Oh, and this was supposed to be a one slight change that I need to make here. This is supposed to be a positive 1. That's a 1. This should be 4. and that should be 4. So that fixes everything. So again, make sure that you change this to 4s, and that's why I underlined it, and 1s at the beginning, because otherwise this calculation does not work. So 1, -7, 3, 0. The bottom row is zeros, and then when I get to the here, I'm going to get 1, -1/2, and 0. So that makes life a lot better. And then one last step here is, let's see if we can get rid of this -7, which we can. So we're going to do row 1 plus 7, row 2. And so on the bottom, we get the 0 rows, 0, 1, -1/2, 0, and then 1, 0, -1/2, 0. So therefore, 1, 0, -1/2, 0, 1, -1/2, 0, 0, 0, 0 times x1, x2, x3 is equal to our 0 vector, which means when we have a row of zeros here, this means x3 gets to be any value that we choose, provided that it's non-zero. And if we solve this, if we multiply these in, I get x1 is equal to, x1 minus 1/2 x3 is equal to 0. Well, this becomes x1 is equal to positive 1/2 x3. And the other equation, when I multiply this row times this column, I'm going to get x2 minus 1/2 x3 is equal to 0. So x2 is equal to 1/2 x3. What this means then is for any x3 not equal to 0, because here, if I let x3 equal to 0, that means x1 and x2 also have to be 0, which gives us a 0 solution, which we cannot have. So we need to choose something that's not 0. We can create a non-trivial eigenvector. So for us, let x3 equals an easy value that we can calculate. We'll say x is equal to 2. So therefore, x1 is equal to 2, 1, 1, or 1, 1, 2. All right. So now we're going to do the exact same thing for lambda 2 is equal to 4 and lambda 3 is equal to -4. All right. So lambda 2 is equal to 4. And actually, let's do this in a different color to keep it separated. All right. So a minus 4i x is equal to 0. So we're going to get, when we subtract 4 from all of those, we're going to get -3, -7, 3, -1, -5, 1, 4, -4, -4. Multiplied by our x2, which is x1, x2, x3, which is equal to 0, 0, 0. Again, going through our process for solving this, set up an augmented matrix, and do some row reduction here. So a couple things, I'm going to do row 3 plus 4 row 2, and then I'm going to do row 1 minus 2 row 2. The reason I didn't go further out with that is just because I can make that a 1 here in a second, and that's going to make life a little bit easy for us. So on our third row, we're going to get 0, -24, 0. On our second row, we have done nothing with it, so it stays the same. And then our top row is negative 1, 3, 1, 0. And now we're going to do row 2 minus row 1, which is going to give us our negatives that we want. 0, negative 8, 0, 0, and negative 1, 3, 1, 0. All right. Next set, I am going to take and deal with the negative of row 1, so we get a positive 1 up there. And then I'm going to do row 3 minus 3 row 2. So that means I'm going to get 1, negative 3, negative 1, 0. Row 2 stays the same, so 0, negative 8, 0, 0. And then we zeroed out our last line there. And then to make things a little bit easier, negative 1, 8th, row 2, 1, negative 3, negative 1, 0, 0, 1, 0, 0, 0, 0, 0, 0. And then finally, row 1 plus 3, row 2. So we're going to get 1, 0, negative 1, 0, 0, 1, 0, 0, and zeros through here. All right. So thus, 1, 0, negative 1, 0, 1, 0, 0, 0, 0, times our vector x1, x2, x3, gives us, well, x1 minus x3 is equal to 0. x2 has to equal 0. So this implies that x1 is equal to x3. So a non-trivial solution is x2 is equal to letting x1 equal 1, so we get 1, 1, and then x2 has to equal 0, and then that is our eigenvalue. So for you guys, work out on your own. Lambda 3 is equal to negative 4, and you will find that x of 3 is equal to 2, 1, negative 1 as your final answer for that part. So again, I'm going to leave this for you for homework. So then that way you guys can work on that. And this is the solution that you should come up with. So our eigenpairs, just to recap everything, is lambda 1 is equal to 0. x1 is equal to 1, 1, 2. Lambda 2 is equal to 4, while x2 is equal to what we just found is 1, 0, 1. And lambda 3, which is equal to negative 4, you guys will find out that it's equal to 2, 1, negative 1. All right, so that's our eigenpairs. Now we need to go to part B, which is do these solutions form a fundamental set? So part B. Again, we're going to use the fact that our solutions are of the form and the determinant of psi has to not equal 0. So y1 of t is equal to e to the 0 times the eigenvector, which leaves us with just 1, 1, 2. y2 of t is equal to e to the 4t times 1, 0, 1, leaving us the solution of y2 is equal to e to the 4t, 0, e to the 4t. And our last one, ys of 3 of t is equal to e to the negative 4t times 2, 1, negative 1, which gives us the vector function 2e to the negative 4t, e to the negative 4t, and then negative e to the negative 4t. All right. So we're going to use Abel's theorem here to help us out. And a version of Abel's theorem is in the previous section. I think 4.2 or 4.3 is where it comes from, is showing that we can use for any value of t in our interval that we can use a specific value of t. So we're going to use Abel's theorem. We can check the Wronskian for some value of t. So let t equal 0. So our Wronskian is the determinant so again, just to give you what that means. So psi here, when evaluated at 0, is going to give us 1, 1, 2, 1, 0, 1, 2, 1, negative 1. Again, these are coming from y1, y2, and y3. So let me put that. That's where those guys are coming from. All right. So we're going to do the determinant of psi evaluated at 0. 1, 1, 2, 1, 0, 1, 2, 1, negative 1. So again, I'm going to go through the calculation with you guys to show that it's not equal to 0. That's what we want to happen. So I'm going to put a question mark there. All right. So we have 1 times its minor. So that's going to be 0 minus 1, so negative 1. Minus 1 times its minor. So we're going to get negative 1 minus 2. Plus 2 times its minor. And so we're going to get negative 1 minus 1 times negative 3 plus 2. So here I'm going to get negative 1 plus 3 plus 2. So we're going to get positive 4, which is not equal to 0. Therefore, y1, y2, y3 forms a fundamental set. And we're done. All right. So that's section 4.4. Again, go through the row reduction for lambda 3, which is equal to negative 4, and you will find that for the appropriate choice, you will find that the eigenvector is 2, 1, negative 1. All right. Y'all have a wonderful day. We'll get into 4.5 here in just a little bit, or whenever it gets posted, and then we'll only have a few more sections left in chapter 4. Y'all have a wonderful day.